Good morning, everyone. Hope you're all well. It's Dr. Bennett here. Today, I've just got a short update video for you about where we are in the semester, what's coming up in the next week or two before the final exam. I'm also going to do a quick review of homework number 4. So let's get into it. So here's the schedule as it stands. Here we are, 15th of April today. We covered distributed loads and internal forces in that example that I gave at the end of the last tutorial. So we've actually done this part for today. Look, bedding moments. So there's really only one proper class left on Friday when we're going to talk about cables. I'll also set the final homework on Friday, which will be due a week on Friday on April the 24th. So between this Friday coming up, the 17th, when we'll have our final class, that's the last time we'll see any new material, is this Friday the 17th. So after that we have these 2 revision classes. So what I intend to do is, so the first request I have is if anybody has anything they'd like to revisit or any specific questions they'd like me to address, then please send me an email and I'll prepare something for either of these 2 days. But basically what I'm going to do is split the semester in half, review the first half on Monday the 20th and review the second half on Wednesday the 22nd. And then that will prepare you. I'll tell you what to expect in the final exam. I'll tell you what to revise, and I'll tell you what the exam looks like. As I've said in a previous update video, it will be an exam of 2 halves. There'll be a quiz, a multiple choice quiz on Canvas for the first half, and then excuse me, and then the second half will be workout problems similar to what you've had for the homework assignments. So so that's where we are, that's where we're going. We're nearly there. So let's have a look now at reviewing homework number 4. So the first question was about the lift on an aircraft's wing, and we modelled the lift with this distributed load, and we have an equation for what that curve, that load curve is, and we're asked to find the magnitudes of the force and the moment about the wing root, which is at point R. So most of you got this correct. So I was basically expecting you all to find these formulae from the notes or from the textbook. We looked at distributed loads in lecture 24, and we said that we can calculate the magnitude of the force and the magnitude of the moment by these 2 integral equations. So if we know the load curve, W, then we can just integrate it with respect to x to get the force magnitude, and then multiply it with x, integrate it with respect to x to find the moment. So pretty sure that 99% of you managed to get these 2 answers here. The next part of the question asked for a free body diagram, now that we know the force and moment, and to determine the reactions about R, which we're assuming is a fixed support. So free body diagram should have looked like this. We have reactions in the x and y directions due to the fixed support, and also a moment about R as well. We worked out the magnitude of the moment due to the distributed load. So we need to recall that the distributed load is lift, right? So we're going to get a counterclockwise moment about R. So that's why I've drawn it on here, positive. I've also put the force vector up here, so in a kind of arbitrary place, just to show that I need to include it in my summation of y forces. We don't actually know the location where this force is acting right now. We just know that it's an upward force of this magnitude. We don't know the x-coordinate of the centroid because we haven't calculated it. We don't need to calculate it, we just need to know the magnitude of it. So that's why I haven't drawn it on a specific place on the wing. We also have the weight vector, which I've calculated here. So what happens when I go to sum my forces? In the x direction I just have this, so I get 0. In the y direction I have this reaction force, this positive and this negative, so I can work out what the reaction in the y direction is. And then summing moments about R, I have this moment here due to the fixed support. I have the moment due to the weight vector, and then I also have this moment. So remember, so a few people included this as well, the moment due to this, forgetting that this moment is the moment due to this force, right? So you only need to include this. So let's go back up here. This moment is the moment about R, or about the origin, right, which is where we set this coordinate system between 0 and L, right? This moment is the moment due to this force. So when we go to resolve moments, we only need to include one or the other. So because we don't know where this force vector acts, we just choose this one, right? And most people were able to find those values down there. So that was question 1. Question 2, let's remind ourselves what that was about. So it was about finding the x-coordinate of the centroid of the volume of the shape below, which was a cylinder with a cone cut out. Now, cylinder with a cone cut out, well, we've seen compound shapes in class number 25, right, when we're talking about centroids of volumes and lines. We saw a compound shape like this, which was a cylinder with a cone attached to the end of it. And we found the x-coordinate of the volume of this shape. And how we did that is we found the x-coordinate of the centroid of both bits, and then multiplied that by the volume of both bits, summed all of that up, and then averaged that over the total volume. So in order to do that, we use the standard results from the appendix in the textbook to find the volume of a cone, the x-coordinate of the centroid of a cone, and the same for a cylinder. Remembering, of course, that the x-coordinate of the centroid, if the shape has been shifted along the x-axis, needs this piece attached to it. So the x-coordinate of the centroid of the cylinder is halfway along it, but we've shifted the whole cylinder by distance a, so we need to add that to it. So remembering all of that, we can just plug it into this formula here, which is basically the sum of the x-coordinates of the centroids multiplied by the volumes of each shape divided by the total volume. So that's for a compound shape where one piece is attached to the other. What happens is when we have a shape with a cutout is we do a similar kind of thing, but we subtract the x-coordinate centroids and the volumes from each other. So we just end up with a negative sign here and here. And this example that I gave in the homework is pretty much exactly like the example 7.75 from the textbook, if any of you had looked through there and had access to the solutions manual, you'd have been able to solve my problem in exactly the same way. But basically, what I was expecting you to do was calculate the volume and the x-coordinate of the centroids for both shapes. So again, these are standard results. They can be found in the appendix of the textbook. A lot of people forgot about that and actually did the integrals, which is perfectly valid, but you could have saved yourself a little bit of work by just using the results in the textbook. Volume of a cylinder, x-coordinate of the centroid of a cylinder, same for the cone, and then plugging that into this equation, which, as I said, is similar to the one for compound shapes, similar to this one, apart from we take the difference of the shape that's been cut out of the main shape. So we have subtraction in here instead of addition, and if you follow that through, you should get an answer of 0.23 meters. So again, the only thing really that you needed to remember here is that the cone had been shifted along the x-axis, right, by this difference here. So the cone had been shifted 0.2 of a meter along the x-axis. Yeah. So the x-coordinate of the centroid is 3/4h, which is the standard result, plus that 0.2. So that's the only real bit that tripped people up with this question. So having said that, I think everyone did really well. Again, on assignment number 4, I think everyone is coping really well with online learning. You're all doing a really good job keeping on top of the assignments, keeping hold of the grades that you had before spring break, if not improving it. So that's really good. So it's impressive that you've all made that transition so comfortably. So well done on that. That's it for today, and we'll get our last class of the semester, which is on cables, done on Friday, and then into the review next week. So that's it for today. I'll speak to you all very soon. Cheers.